Hello fellow tech enthusiasts. Welcome to our new course in the Zero to Hero series. Today we'll explore microservices. As part of the Zero to Hero course series, we aim to equip you with the knowledge needed to excel in your implementational use case, ace interviews, or tackle exam questions. If you have any doubts or if you believe we are overlooking any important concepts, please leave a comment on this video. We will address it. Let's review the course outline first. Before explaining microservice architecture, we'll explain what is monolithic architecture. Then we'll go to challenges of monolithic architecture. Then we'll come to what is microservices and all other associated concepts. We'll see microservice benefits. Then we'll compare monolithic versus microservices versus service-oriented architectures. As part of module 2, we will dive deep into microservice architecture and we will review microservice communications. Then we will review microservice design patterns. We will start with service registry pattern, then we will discuss circuit breaker, then API gateway, followed by event-driven architecture, and then database per services. These are the top 5 design patterns. If you want to understand any other design patterns, or if you want me to cover all available design patterns, please drop your comment. I'll create a separate video. Then we'll review challenges of microservices, followed by microservices code repository, then microservices antipatterns. We'll navigate to module 3 and we'll review observability and monitoring aspects. We'll start with microservice monitoring, then distributed tracing, then error handling strategies, and then we'll navigate to module 4 where we'll concentrate on security considerations. We'll start with security challenges for microservices, then microservice security best practices. Throughout this course, we have used real-life examples, animations, and hands-on experience to make this course effective, interactive, and easy to understand. If you encounter any challenges to understand any concept, please note down the timestamp and leave your comment. I will do my best to clarify the concept for you. We have a lot to cover. Now let's jump right into it. First, we'll start with what is monolithic architecture, and for this we'll take an example of insurance application. In our day-to-day life, we use multiple insurance starting from car insurance, renter insurance, health insurance. Let's assume one of that insurance application. Now in terms of insurance application modules, we should have a product module. Then there should be a quote or illustration module. Before taking the policies, we are creating those quotes. Then policy generation, followed by payment module, that is another one important module. Then claims, and last but not least, policy servicing. There could be other modules available also, but on a high level, these are the modules let's assume that we have for our insurance application. As part of monolithic architecture, there is a single code base for all these modules. This leads to application must be deployed in one technology stack. Now, if we go on the layered architecture, maybe we will have a UI component followed by all the business logic, one single application code for all the business logics, then the database access layer, which will be combined as a application services, and then there will be a database. This is on a high level 3-tier architecture for a monolithic architecture. And here what we saw, everything is deployed and developed as one single package. Then the entire application must be redeployed. Let's say you have some changes in the payment module. Even if you have a small change in the payment module, since the application is built with a single code base, entire application must be redeployed. And developer must maintain functional integrity. That means when we are changing in the payment module, that change should not include or introduce any error or bug to other modules. Then let's review what are the challenges of this monolithic architecture. Left hand side, this is a low level diagram that I have created for the architecture diagram. To start with, The first challenge is lack of scalability. That means all the components are tightly coupled that require to scale the entire application. Let's assume that maybe you are getting a lot of traffic for the code module. That means many users they are generating the code, and that is creating a good amount of traffic to your application. Although only the code module is using, you won't be able to auto scale only the code module. To auto scale your entire application, you have to auto scale the entire application server, which leads to insufficient resource utilization and increased cost. Then there will be limited technology flexibility. We have to use single tech stack throughout the application, and that will lead to hinders adoption to new technology stacks. If we'll try to understand using an example, let's say in my claims module we are using JAX-B 2.2.4. In the payment module, if there is a requirement to use JAX-B 2.3.1, because I am integrating with external payment gateways, my current application will create conflict. In this case, either I have to upgrade JAX-B for the entire application module including claims, or else I have to find a down compatibility for the external services or the payment services for my case. Then lack of deployment agility. That means developers will work on the same code base. Although if you have a separate team for the product or for the claims, for the policy servicing or even for the payment, all the developers they will work on the same code base, which will require rigorous testing and regression testing at the application level whenever there will be a small change. Then the deployment complexity. Since we are deploying the entire application, any small change will require the entire application to be deployed, and that needs the entire application to be tested after each and every deployment. That will lead to longer deployment cycle and increase downtime. Last but not least, there will be maintenance challenges. Challenges will be to understand the component dependencies. As multiple modules all are accumulated in one big code base, we have to understand which module is dependent on what. If I want to change any code or introduce any new libraries into policy module, I have to make sure that new library will not create any library conflict for other modules. Then you must be thinking, what is the solution for this? The answer for all those challenges is microservices. Now let's review what is microservices. We saw for a monolithic architecture, we have a single big jumbo code base which consists all the application modules. Now in microservice architecture, we split that monolithic application into smaller independent module that will lead to small modules for each and every independent services. Now that may trigger a couple of questions. How to split the monolithic application? What are the specific functionalities that the system needs to provide? What is the optimal number of services I should create from my monolithic application? How to logically separate the services to minimize dependencies between modules? How will the microservice communicate with each other? And what database or data store will be used for each microservices? Let's try to understand answers for all these questions. We will start with how to split. When you will have a monolithic application, the splitting from monolithic to microservice should be based on business functionality, not on technical functionality. If we'll use our previous example, when we saw that insurance application, we had product, policy, claims, quote, payment, servicing. These are all business functionalities. If we want to convert that to microservice architecture, we may create separate services for product, policy, claims, quote, payment, servicing. Like that way, we have to create separate modules for business functionalities, not on technical functionalities. Then in terms of number of services or how to separate the logic, we have to remember that these services should be independent and it should be for a specific job. Claims and payment, these are specific jobs or specific business functionalities. We should create two separate microservices, one for claims, one for payment. We should not merge them together and create one service for both claims and payments. Each service must be developed, deployed, and scaled independently. Services must be loosely coupled. They should not have any dependency with each other. Let's assume that we have this microservice architecture where we have separate services for product, policy, claims, quote, payment, and servicing. Now, if we want to deploy one service, let's say policy service, we should build and deploy it separately. There should be separate pipelines or CI/CD pipelines which will deploy only the policy service. It should not deploy the entire application or all other services. Services will have independent release cycle and version number. As we discussed, since we will have separate CI/CD pipelines, services can be deployed independently. They can have their own release cycle that will lead to different version numbers as we are displaying in our example. Now let's review what are the advantages of microservice architecture. To start with, the first benefit would be modularity and scalability. This modular approach enables teams to develop, deploy, and scale services independently based on their individual needs. It will offer the flexibility to add, remove, or modify services without affecting the entire system. Then it will be easier to adapt and evolve application over time. As we discuss the disadvantages of monolithic architecture, if we have to maintain two different service version or library versions, we will be able to easily manage and maintain in microservice architecture. That will lead us to easier adoption and evolve the application over time. Then scalability and flexibility. Since all those services will be managed, maintained, and deployed independently, for our previous example, let's say if your application is getting more and more quote requests, we'll be able to independently scale this quote module. This scaling will be horizontal scaling. We do not need to increase the RAM size or CPU size or even to replicate the entire code. We can only scale the quote module. That will lead to efficient resource utilization and cost optimization. In terms of technical heterogeneity, we already discussed each service can be deployed using different tech stacks because there is no dependency or those services are not part of a single code base. It will be easy to adopt new technology without disrupting the entire system. If we want to introduce any new library to quote module, the changes will be localized to quote module and that will not trigger any problem for other modules. Then continuous delivery and deployment. Independent team can own individual services as there is no dependency. Each service can be independently tested, integrated, deployed, and that will enable us frequent deployment. And one thing we have to remember, we are eliminating the regression of the entire application if we want to change one code or one small functionality in one particular module. This leads to reduce the risk of introducing new defect and it will be faster time to market. Now teams can work independently and release the services without depending on other teams. Before we proceed further, I would like to request you, if you are new to our channel or haven't subscribed yet, then please consider subscribing our channel and please click on the bell icon to get notification for any new topics. Let's continue with the video. Now we'll compare microservice architecture versus service-oriented architecture. When you are talking about the microservice, I feel some of you may feel that this is somehow similar to SUA architecture or service-oriented architecture. Now let's compare side by side. As the picture suggests, for service-oriented architecture, it will have an enterprise service bus, ESB, whereas for microservice architecture, it will have a service gateway. For microservice architecture, the service gateway could be a load balancer, it could be API gateway, anything which can cater the request to different services. For communication between different services in microservice architecture, we can use either REST API or message broker, whereas for SUA architecture, for communication, we are using ESB layers. for microservice architecture, we use lightweight protocols such as HTTP REST protocol, whereas for SOA architecture, it supports multiple message protocols. Microservice architecture mostly cloud native, and nowadays we are not managing or maintaining application servers for this microservice architecture. Whereas for SOA architecture, we use a common platform for all services. And still, if we are using on-premise, there we are using SOA architecture. Microservice architecture will have a relaxed governance with greater focus on teams collaboration and freedom of choice. Whereas for SOA, there should be a common governance and standard. Now let me take an example. Let's say your web tier want to communicate with service tier. If there is any change on the interface, there should be a common protocol for input request and output request. That data pattern, it should be there. Somewhere we are using that CMM standard. That will lead to a common governance and standard we should maintain for a SOA architecture. Now I have this side-by-side comparison for service-oriented architecture versus microservice architecture. If you want to do a deep dive and you want to know those differences side by side, you can pause the video here and read those side-by-side comparison. Next, we'll navigate to microservice communications. What are the different ways all those individual modules can communicate with each other? First option, we can use API calls or RESTful APIs for inter-service communication. In this method, all microservices modules will have their own API endpoints. As an example, for product module, after the domain name it will have /product. For quote module it will have /quote and so on. To communicate, services will send the HTTP request to the corresponding service endpoints. Let's assume the policy module is trying to communicate with the payment module. Policy module will initiate a HTTP request. The payment module will process that request and will return a HTTP response. This is an example of synchronous communication. That means the invoking service will wait for the response. For our case, once the policy service will initiate a HTTP request, it will wait for a HTTP response from the payment module. The next communication technique could be using a message broker. Let's say we have our producer application or the policy application. It wants to communicate with a payment module, and for our case, this is the consumer application. Now in this communication mechanism, we can use a message broker. It could be a RabbitMQ, it could be a Kafka, or any message MQ or message broker we can use. Now the producer will initiate a request. The request will be queued in the internal request queue, and then the request will be passed to the consumer who will process that request. This is an example of point-to-point. In PubSub module, producer will put the message to a common queue, and from that common queue, it will be distributed to all the consumers who are subscribing that queue. Whereas for point-to-point, there will be separate queue for each communications. This type of communication is asynchronous communication. That means invoking service will not wait for the response. Now you might be asking, if my policy service is invoking payment service, then how the response will come? If you need a response from the consuming service, then you can create a separate reply queue. For our case, the producer module will first put that request into request queue. Then the request will be passed to the consumer application. Consumer application will process the request and create the response, and it will send that response or post into a reply queue. Then the reply queue will push that response to the producer application, or in our case, policy module. This is the way we can create both way communication, and if you want to establish both way communication, you need separate queue. Navigating to the third module, that is service mesh. Service mesh is most common when we are using Kubernetes or Kubernetes containers. In that case, we have two components. One is the data plane. Now, data plane is made of services. For our case, we have quote, payment, claims. Now, these services will run alongside with a proxy in sidecar pattern. These services will handle all those business logic, whereas the proxy, it will sit between them and it will establish the communication with other module or external module. Now all the traffic, it will be ingress, egress, that will occur through those proxies and which are responsible for routing traffic to other modules. So data plane is made of services running alongside with sidecar proxies. Now there is a second component which we call as control plane. Proxy configuration is done through the control plane, which will provide the administrative functionality over the service mesh, and it will provide an interface to configure the behavior of the data plane and for the proxies to coordinate their actions. To summarize, we have seen three communication patterns. First one was using API call, then we have review using message broker, and third is using service mesh. Next, we'll move to microservice design patterns. To start with, first the service registry pattern. As the name suggests, there will be a registry for all the services. Let's try to understand using one example. In our example, we saw we have quote module, claim module, payment module. And let's say if our application is getting much traffic for the quote and some traffic for the claim, as part of microservices, we can independently scale them. Now, after we scale, let's say my architecture is like that, and each module will have their independent IP addresses. Now we have a service gateway which is catering the request from client to all those services. Now how my service gateway will know which service is available or where to pass that request? Once I'll have all those quote modules or the auto scaling has done, I have multiple modules. And now instead of sending only one quote module, all the requests would come to the three modules or into the three IP addresses. Similarly, when one service will go away, no request should go there. That means we need a registry which can hold all those mapping. And to address that, there will be a service registry which will hold the mapping of the services with the IP addresses. And once a new request will come, service gateway will ping service registry. It will get the IP address. Service registry will pass the IP address from the mapping. Now service gateway can cache that IP address. Maybe there will be a TTL or time to live for the caching, or else new request will not be able to discover or new modules will not be discovered, and according to that IP address, the service gateway will pass that response. Now here the main factor is each services must register or deregister with the service registry. When you are doing an auto scaling, when there is a scale out event, new services will be launched and it should register with the service registry. When the traffic will go away or once the service will be scaled down, that time the module which is going down should deregister from the service registry. Netflix Eureka is a very popular example of the service discovery pattern, and Netflix Eureka can be widely used with Spring Boot and other modules as well. But I believe now by this time you are getting a feeling whatever we are doing here, maybe Kubernetes orchestrator or application load balancer is doing the same thing. Why do we need a separate service registry? You are absolutely correct. In today's world, container orchestration system or even the cloud load balancer automatically handle the service registry. That is why service registry is going to fade away and this is losing the interest. That means as we saw in the cloud load balancers, there will be target group. When new target will be launched, it will register and there will be health check. Cloud load balancer or container orchestrator, they have implemented the service registry pattern. The next pattern is circuit broker. Let's say I have service 1 which is invoking service 3 and service 3 is dependent on service 2. Now let's assume that service 2 has some error. So service 2 is not sending any response to service 3. Now once service 1 is invoking and service 3 is not getting any response from service 2, service 3 will send error response to service 1. Now service 1 does not know that service 2 is down or service 2 is not responding. Service 1 will bombard with request to service 3, which will lead to network resource congestions. That means all the network resources will exhaust it and it will lead to low performance or bad user experience. Now, it can lead to failure of one service, it will lead to cascading effect. How? Let's say my service 3 is not responding properly, that is leading to service 1 is also waiting. Now, if there are other services which is depending on service 1, or maybe service 1 is doing some more external APIs call, all those API calls can also get halted because service 1 is waiting response from service 3 and it can take the entire bandwidth. So this will lead to a cascading effect. Now, how can we stop that one? We can stop using a circuit breaker. The name suggests it just work as a circuit. There are three stages: close, open, and half open. Once that state is closed status, that means all the requests will go from service 1 to service 3. That means the path is established. The moment the status will be open, that means all the connection will be teared down here and service 1 will not be able to invoke service 3. That will lead us not to exhaust the network resources. And half open means we can pass some of the response to check if the service 2 is available or if service 3 is responding. Now let's try to understand using this diagram. Currently I have the circuit as closed. That means all the requests from service 1 is going to service 3. Once service 2 encounters some issue, service 3 is not responding, or service 3 is not responding because it is not getting any response from service 2, then we can open that gate. That will lead any request from service 1 will be hold and it will not reach to service 3. Now after that, after some time, we can make it half open. We can check with a subset of the request if service 3 is back or service 2 is responding or not. If we see that service 3 is available, it is responding properly, then from half open we can move to closed state. But if we see that no, service 3 is still not responding, it is still giving some error, maybe we can again go back from half open to open state. Next is API gateway. As the name suggests, we can have an API gateway in front of all those services. Now this service can have their independent databases and all. Once the request from the client application is coming, it will first land to API gateway. API gateway will work as single entry point for all the API requests and it will encapsulate the underlying system architecture. In this case, you can see the API gateway is working as a reverse proxy and it will redirect or route the request to internal microservice endpoints. Now we can configure with authentication, SSL termination, cache, or even rate control. If we want that, okay, maybe my code request, it cannot be invoked more than 10 times per second. We will be able to create the rate controls. Or maybe if we have the same response we are passing through, we can configure the caching. Also the SSL termination and authentication for the security reasons. Then there are a couple of popular examples like MuleSoft, Azure API Management, AWS API Gateway. Those are popular services where we can implement the API Gateway design pattern. Next is event-driven. Before I explain the event-driven, let's try to understand the conventional design pattern. Let's assume I have a client application and here I am taking the claims module. Client application will upload the claim documents and the claim documents will come to a network storage area. Then in that claim module, there is a scheduler which will scan the network storage frequently or after certain schedule. Maybe after 5 minutes, 10 minutes based on the schedule. Even if there is no document, then also the claim module is scanning that location. If it will get any document, then it will process the claim. Maybe it will first send a acknowledgement or send a notification to the claims department and then it will start the processing. In conventional architecture diagram, we can understand maybe during the daytime, claim can come only few times if the application is not that popular, right? Still, we have to utilize that modules or still we are using those resources and scanning that location. We can eliminate that using an event-driven architecture. In event-driven architecture, still our client applications will upload the claim document into some network storage. But in this event-driven case, this will work as the event source. Instead, the client module is scanning the location. My event source will publish an event as soon as there are some documents available, and that event will be queued into event bus. Then the event bus will trigger the claim module, and the claim module will then send an acknowledgement or it will start processing the claim. Even we can invoke the acknowledgement notifications and the claim processing together from the event bus. This will allow us high scalability as new services can be added without affecting the existing one. Since we have an event bus, we can add more processing layer, and if we are using pub/sub model, we have to just add them as a subscriber. This will lead us to decouple of services and loose coupling integration. Now my network storage and claim, there is no dependency there. Today maybe I have a S3 bucket. Tomorrow I can go to a different blob storage, Azure blob storage. And by this way I will be able to change. Only thing is required that I have to publish an event. Navigating to our last design pattern for our course, database per services. As the name suggests, every module can have a single database. There could be other patterns. Although we have broken those monolithic application into small microservices, then also we can use a single database. But database per service means every module will have their separate database, which will lead us, we can either select a NoSQL database, RDBMS database, or we can use the combinations. That means all those modules can have independent databases. Now each database can scale independently. If one database server is down, that will not affect other services. Unlike the previous model we discussed where we have a single database. If the database is down, that will lead to all the module will affect the performance. But one point we have to make sure, since we have separate databases module wise, we have to implement transactional atomicity. Because let's say if I am trying to create a policy, first my payment should process, right? If the payment is not processed, I should not issue that policy. So that is how I should implement the transactional atomicity when I'll implement or when I'll segregate the services based on their business functionality. Next, we will review microservice challenges. First, since this is a distributed system, that will include all the distributed system challenges. It may introduce potential issue related to network latency, service discovery, message format, handling different failure scenarios, or even data consistency. Since all the modules are communicating with each other, it can create network latency. Since all the modules are separate and we want to communicate maybe with public internet, that can add some network latency. In contrast, if all the applications is one application server, maybe those module communication will be much faster. There is a challenge to monitor, logging, or even troubleshooting. For Monolithic, we have one application server, all the logs in the one place. We can debug that code, but in a microservice or distributed architecture, we'll have different logs. There could be cascading functions. We will see that in a different slide. But sometimes the troubleshooting can be little bit complex. Then data management. Since we have dedicated database, that can lead to data consistency issue and data integrity challenges. We may need to add custom coding, or we may need to add additional overhead to coordinate those transactions and maintain data consistency. There could be some deployment complexity also. As we are upgrading those modules independently, it can create some backward compatibility issue. Let's say in my code module, if I am deploying the code module separately, and I have to make sure all other module which is invoking my code module should be backward compatible. I should not change in the interface that can break other modules. Next, the microservice code repo. When we have the monolithic architecture, all the code was in a single code repo. Then for microservices, how can I manage the code? What are the options I have? We have two options. One, Monorepo. As the name suggests, I can have a single repository to store all the modules, or else I can create multi-repos. As the name suggests, I will have dedicated repository to store individual modules. Now let's review one by one. We'll start with Monorepo. We saw Monorepo is a single repository to store all the modules. That means we'll have a directory for each service module or a folder structure. Let's see an example. Let's say in our car insurance application, we have claims, payment, policy, product, code, servicing. This will be part of one code repo, and all individual modules will treat as a folder structure in our application code. Now, what are the benefits? All the codes are centrally located, and that is how it will be easy to manage. We can have shared code and configuration files between the claim, payment, policy. If we have any shared configuration files, we will be able to utilize that. We can clone and deploy with one repo. Let's say if I have a small team who are managing all those codes, they can clone that repo once and they can change on the respective modules, and then they can push those changes. This makes the code management and deployment process easier. Let's say if you want to refactor any code, then it will be painless application-wide refactoring since all the codes are in one place. But there are some challenges also in this approach. And now let's review the challenges. First challenge will be we need to require the entire code base. Now let's say if you have a fairly big application, all those module code base are not a small code base. In that case, it will take a longer time to clone, it will take a longer time to manage. That will lead to tight coupling of project, and it's easier to break other modules since we are using shared code or configuration. Changing to one module can lead to introduce bug to other modules. Let's say I have multiple libraries that we have used. Now when you are tagging those code base, we can have some libraries that is not used, and once I'll add the tag, it will add tag to all components, and that will lead that unmodified libraries or unused libraries also could be part of that versioning. Since we have all those modules as folder structure, in terms of CI/CD pipeline, if you are using GitLab CI/CD or other CI/CD pipeline, normally we can have one CI/CD pipeline from repo wise. Now, if I have only changed to the policy module or to the payment module, I have to create custom logic such that my CI/CD pipeline can detect only that payment module, and it will deploy only the payment module. It should not deploy other modules also. If you have multiple teams, they are working on multiple modules using a single repo or monorepo, it will be difficult to implement granular access control. Now let's review how we can overcome those limitations using multi-repo scenario. In multi-repo, we have dedicated repository to store individual modules. Now let's see an example. Unlike to my monorepo, I have dedicated Git repo, one for claim, one for payment, one for policy, like that. And here what we can use the group feature, the repository group feature. Like in GitLab group, we can use the group feature to group all my repos under one group. In terms of benefits, this code is completely isolated. We can clone and deploy services or the modules independently. We can have independent library versioning. We can provide granular access controls. Since we have dedicated repo, we can implement granular access control. We can have independent CI/CD pipeline. The previous limitation is no longer a limitation in this case because I can establish a dedicated CI/CD pipeline from each repo. Now there are some challenges also. In terms of challenges, if I have only one team, they are working on multiple modules, then switching between the project, it could be a tedious effort. Now searching, testing and debugging will be more difficult because I will have multiple code repos. There we have to create separate merge requests for each and every repo. That can lead us to multiple merge requests or overflooding merge requests. Now we saw that both the approaches have benefits and challenges. Now the question would be, what is the scenario to use multi-repo versus the monorepo? If you have a smaller code base or smaller application, you can go for a monorepo approach. But when you need a dedicated pipeline or separate release process, or if you have a distributed team and need granular access control, that time you can go for multi-repo approach. Next, we'll review the microservice anti-patterns. The first is monolithic microservice. That means we have broke down that monolithic architecture into microservice, but we haven't truly decoupled the components. Maybe each microservice is tightly coupled to each other, and that will forfeit the entire benefit of microservices. If I'll take an example, maybe shared database structure. We have all those services we have segregated into microservices, but all the services is connecting to a single database. Obviously, this is not a good microservice architecture pattern. Then chatty services. Let's say all your internal services, they are communicating excessively. That can often lead to high volume of network calls. It can increase the latency, it can reduce the performance, and it can overhead the network. If you have chatty services, or if you need a tedious amount of inter-service communication, maybe that two services is not a perfect candidate for a microservice. Then shared libraries. If you have shared libraries or common libraries across code, across microservice modules, or maybe if you have tight coupling between those microservices, that will make it harder to upgrade or evolve independently, and that will forfeit the microservice advantages. Last but not least, if you have ambiguous boundaries, that means when you have designed that microservices, you have poorly defined the boundaries between the microservices, which will lead to overlapping functionality or unclear responsibilities. That will cause the confusion, duplication of effort, duplication of code, and difficulty in maintaining and evolving the systems. Next is microservice monitoring. Let's assume I have this distributed architecture where I have browser or the web applications and the mobile applications. I am using both API gateway, and also I have a login module. And here is all those independent modules with a dedicated database. Once I'll encounter some issue, how I can manage, monitor this application? First, we have to do a service health check. This is a proactive measure, not a reactive measure. That means we'll periodically do health check for each individual modules. This health check will help us to identify issues early, and it will prevent them from impacting the overall system. Next is metrics collection. As part of the service health check, we can collect different matrices like request per second, failed request per second, or the error rate, or the average response time, average execution time, maybe success or the failure rate. Maybe we can go for the request latency, or maybe we can use CPU uses, memory uses. All those metrics we can monitor. And as I mentioned, these are the preventive actions, not the reactive actions. We can also go for the logging and tracing. That means we can add relevant logs from the events, error, exceptions. Also, we can generate service map or the request tracing. We saw that this is the high level. All those components, we can create a service map for all those components, and we can create a trace map that will help me to detect from which component the failure is coming, or which component is showing a latency, or which component is not responding properly. And last but not least, we can add alert and notification. Again, this is part of the proactive monitoring. We can create or set up automated alerts, maybe text message, maybe email message, based on the predefined thresholds. If we see that my error rate is go above certain percentages, or maybe my request latency is going above the threshold, then we can create text alert or the email alert to the corresponding team, such that they can have a look that application. Now, whatever we have talked, all those monitoring, AWS CloudWatch or the AWS X-Ray, previously AWS X-Ray was a separate service. Now AWS X-Ray has been merged with AWS CloudWatch. Now if you go to CloudWatch dashboard, and if you enable AWS X-Ray, or if you are using the X-Ray agents, then you can get the service map. You can see all those red highlighted sections. So these represent that there is an error. And also it will give us the average latency, average request processing time, and the entire service map. So which service is faulty, from where the error is coming. It will give a good level of details. Navigating to microservice error handling, this is more on the reactive feature. We can implement mechanism to detect fault and failures. Accordingly, we can isolate the faulty component that will help us to prevent cascading failure for the entire infrastructure. We can also configure retry and rate limit. We can implement the automated retry and exponential backup. Let's say if one service received response, maybe instead of retrying instantly, we can wait for 2 seconds. If again that failed, maybe we can wait for 4 seconds. So we can take some random numbers and automatically we can retry using the exponential backup. Also, you can implement circuit breaker pattern. We have already reviewed circuit breaker, and that will help us to proactively monitor and prevent requests to reduce the load on the unhealthy services. We can also implement fallback mechanism to handle the degrade or the partial responses. We can use cache data, or we can returning to default values, or even we can redirect the request to an alternative services when my service is throwing exceptions. We can also go for a graceful degradation mechanism. That means we can prioritize the critical functions and we can ensure essential services remain available even under that adverse or the faulty condition. As an example, let's say your application has premium users and the general users. When your application is facing error, maybe you can only serve the premium users since they are paying a premium charge. Maybe by that time you can redirect all your general users to a default page or to an error page while serving only the premium users. That will lead to service isolations, availability of your application in case of errors or diverse scenarios. Next, we'll review the security challenges of microservice architecture. First, increase attack surface. In our monolithic architecture, we had only one application server. In microservice, it's a distributed architecture that will lead to larger attack surface and prone to different types of attack. Different exploits or vulnerabilities, it can attack to a particular module. If it is a broken link in the security chain, it can attack to that particular module and it can gain unauthorized access, or it can compromise my sensitive data. Now in monolithic application, we saw all the modules in one place. That means the inter-module communication is not going beyond that server. But for microservice architecture, intercommunication, it can go over public internet, which can lead to eavesdropping, tampering, or even man-in-the-middle attack. That is why in microservice architecture, the inter-service communication is very crucial and we should prevent unauthorized access or data breaches. Next is data protection. Microservices often manipulate and exchange data across network boundaries, and that will increase the risk of data exploits or leakages. That is why in microservice architecture, we should ensure proper data protection mechanisms such as encryption, access control, data masking, which are essential to safeguard the sensitive data. Before we conclude our today's video, we'll review the microservice security best practices. To start with, we should enforce a strong authentication and authorization mechanism such as OAuth or JWT token, and that will help us to authenticate the user or even the services that is communicating with the microservice. We should implement a fine-grained access control and we should enforce principle of least privileges. We should secure inter-service communication using HTTPS or TLS or SSL certificates, and that will help us to encrypt the data which is going beyond or which is exposing to public internet. We can also implement mutual TLS for service to service authentication, and also we can implement encryption to prevent unauthorized access and tampering of the data. We can apply defense in depth approach. That means we can adapt a layered approach to security by implementing multiple level of security controls. Also, we can combine network security, application security, infrastructure security to create a robust defense in depth strategies. Last but not least, we should implement a regular security testing and vulnerability management process. That means we should conduct regular security assessment, code reviews, penetration testing to identify and remediate security vulnerabilities in our microservices, and we should implement a vulnerability management process. That was all for today. If you like our effort, please give us a thumbs up and please share this video with your friends and families. Subscribe to our channel and please click on the bell icon for more content like this. Thank you for watching.